Yeah, hello. So, welcome to this session on the course of Introduction to Machine Learning, and today's it will be about week 12 in the lecture. So, in the week 12, there were 4 lectures, out of which 2 were optional. So, only some introduction about some basic introduction about reinforcement learning was there in the second lecture, and some topics about learning theory were there, but I guess the questions that will be asked from these places won't be that difficult. I will be, as always, I will be going along, I will be solving the questions that were given for this particular week in the last run of the course, and I'll also discuss the answers with you all. And once I finish, you can ask me other questions that you have. In the midst also, if you have any doubts, you can stop and ask me. Okay, so the first question is, okay, let me check whether I'm recording. Yeah. Generalization error is given by E of H, where P of x and y, where x and y comes from a particular distribution, and wherever so H is the hypothesis that you have, y the true labels, and H of x is therefore the predicted labels, let's say, right? So in such a situation, the error that you get for the particular hypothesis is given by P of x, P of the probability of Hx not being equal to y, where x and y is basically comes from a particular distribution. So the question is, what is the distribution from where you draw x and y? So x and y will obviously be the distribution which you are trying to estimate, because you are given samples from a particular distribution. The entire topic of machine learning is about finding out what the distribution is from which you were given the training samples, and therefore the underlying distribution which we are trying to estimate is actually the distribution from which you will draw x and y. Okay, that is fine. Then the hypothesis function obtained by empirical risk minimization is denoted as so as this was also shown in the lecture, that this is the ERM formulation. So empirical risk minimization is also known as ERM. So this is the ERM formulation, and ERM formulation tells us that, okay, so among so this epsilon h is the same as this, right? So whatever epsilon h you get, you among all your hypotheses, you pick the one hypothesis for which this error becomes the least. So let's say if H is a class of neural networks, so this H belongs to H is basically, this is a set of hypotheses, and so this can either be let's say a linear classifier, right? This can be SVMs. This can even be neural networks. This can even be neural networks. So in such cases, what we have is, so suppose if H is a class of all neural networks, which aspects constitutes this space? So this particular way in which you are doing the ERM formulation, so the ERM formulation is constitutes, so how can I say this? Yeah, so ERM formulation is something that when you solve it, you get some realization of your hypothesis. So in other words, ERM formulation is something that suppose you solve the ERM problem. Now once you solve the ERM problem, it will give you something, it will give you some answers, the answer that you get from the ERM problem is actually a realization of your hypothesis. Now if let's say different number of layers, if the number of layers itself is part of your so if H is a class of neural network, which aspects constitute its space? So of course you can understand that this would be the error, epsilon H would be the error, and you need to minimize that error so that you get some particular neural network. And when you have been taught neural networks, you have seen that the number of layers that is there in a neural network is basically a hyperparameter. It is not something that you can get just by doing gradient descent or backpropagation, and therefore number of layers cannot be a constituent of the space of your in the space of your hypothesis. For example, you cannot have 2-layer neural networks and 3-layer neural networks in your hypothesis. You only need to have a single, either all 2-layer neural networks or all 3-layer neural networks in your hypothesis space. Okay, and for the same reason, different number of neurons also per layer cannot be a factor, because when you solve the ERM problem, you cannot have the number of neurons per layer to be variable. And different values of weights, this is something that is correct, because you have seen in the backpropagation algorithm, when you solve it, you end up with weights for the neural network that you had started with, and therefore different values for weights is a correct answer for this particular question. And different inputs, that is not even a question, because you are searching over the space of hypothesis, so different inputs doesn't make any sense here. I hope that was clear. Then the next question is the Chernoff-Hovting bound. This is a strange bound, and you might have to learn it by heart for your exam. Okay. So this is a bound that has been used in the class quite extensively. So what it effectively says is, you see, the problem is E of epsilon of H is basically the error when you have the true distribution. However, while training any machine learning model, you will only be given some samples from this training distribution, from this true distribution, and therefore what you estimate will actually be epsilon hat of H. So this is the actual error that you would have got if you had taken the actual distribution, and this is the sampled distribution that you have taken, and therefore epsilon of H minus epsilon hat of H, you are always keen to find out that the error that I am actually seeing in my training data, how close it is to the actual data, and the probability of that being differing by on either sides by a constant of gamma or by a value of gamma is has an upper bound of 2 e to the power minus 2 gamma square m, where m is the number of samples. Okay, so so basically you test it. Now the question says you test it and find that increasing the number of samples does not give a more accurate estimate. So in other words, what you are seeing is you are increasing the number of training examples, however this the difference between epsilon H and epsilon hat of H is not coming down. It's not coming down. So what does that mean? Choice of gamma is unsuitable. That is the first option. Now of course gamma is something that you want, gamma is something that you would, it's not like let's say the epsilon H and epsilon hat of H is very, they are widely different from one another, and you increase gamma to such a value that and you or rather you you decrease gamma, let's say you decrease gamma or you change gamma in such a way that this bound always holds for that particular m, and so that doesn't give you anything, right? The entire point of this happening is, given a gamma, you are given this gamma, whether you can increase m to bound this particular difference. So choice of gamma is unsuitable should not be a way in which you give a more accurate estimate, because if you change your gamma, your estimate, the accuracy of your estimate itself is changing. The mean is not from Bernoulli distribution, again it is not a point here. Then choice of hypothesis function is wrong. So if you don't look at this from the point of view of this equation, but just think of this from a normal machine learning perspective. So I'll talk about this here maybe. So you see what is happening here is training data increasing in size. That this is something that you are doing, but error not coming down. So whenever you see this sort of a thing, like whenever you see this sort of a thing, even while training your models, the first attempt that you should do is your hypothesis or your model needs to be made stronger. Suppose your training error is not coming down even after after increasing the training data. So that means that your model is not being able to learn the distribution at all. In such a case, your model needs to be made stronger. In learning theory, the other way of saying this is choice of hypothesis function is wrong. Your hypothesis or your model that you had started with was wrong for your particular estimate. And the samples are not IID. This is another, this is purely from the basis, I mean this equation holds if the different hypothesis that you are looking at are all IID, or the different samples are all IID, the different training samples are all IID, but if that is not the case, then this bound anyway does not hold. Some complicated things appear at that point of time, and therefore this bound will not hold, and therefore samples being identically distributed and independent is a necessity for this particular bound to hold. Okay, the proof of this bound is out of scope of this particular course, that can be found, I guess, in some probability textbooks. Okay, then the next question is reinforcement learning. It's a assertion reason type of a question. So the question is, reinforcement learning is a type of unsupervised learning. Of course, this is not true. We have three types of learning: supervised, unsupervised, and reinforcement learning. And reinforcement learning does not have labels. Reinforcement learning does not have labels is actually true. Therefore, statement A is false, statement B is true. Okay, aliens. Then the next 3-4 questions are all on reinforcement learning, the basics of reinforcement learning. So aliens challenge you to a complex game that no human has seen before. They give you time to learn the game and develop strategies before the final showdown. You choose to use machine learning because an intelligent machine is your only hope. Which machine learning paradigm should you choose for this? Of course, the answer would be reinforcement learning. You can't use supervised learning because no human has played it before. Unsupervised learning, because unsupervised learning is something that, I mean, so unsupervised learning and reinforcement learning are different in the way that you have some amount of feedback in reinforcement learning, but in unsupervised learning you have no feedback at all. Okay, so reinforcement learning is the correct option here, and use a random number generator and hope for the best is of course not a correct answer. So in the Pavlov's dog experiment, so what he used to do was he used to put a bell, he used to ring a bell, and then he used to feed the dog after that bell. So the dog got conditioned that after hearing the bell he would get some food. So the input signal to the dog is the bell, and the reward is food, because the dog is listening to the bell, and then whenever it is listening to the bell, it knows that it will now get the food. It will go to some place and then it will get the food, and therefore the input signal is bell and the reward is food. What is a policy in reinforcement learning? So reinforcement learning, if you think of it in a very broad sense, it is like you have particular states you have these states where you can be at any one point of time, and the action that you do to go to the, so this is, let's say, at time t1, and this is at time t1 plus 1. So what the so given that you are in this state, the what is the, I mean, what action should you take means which state you should jump to in the next time instant is something that is known as policy, and therefore a mapping from states to actions. The action is this jump, this is the action here. So a mapping from states to action is known as a policy in reinforcement learning. These are all very simple questions directly from the course, directly from the lecture. Then the last question is, you want to make, again this is directly from the lecture, you want to make an RL agent for a game where two players compete to win, like chess and go. Which among the given would be the best approach for this? Play again best human players. That is of course not the correct way, because so you can think of an RL agent as a child. So a child, when it learns to play chess, then of course he cannot play, you cannot put the child against a grandmaster of chess, for example, because he or she won't learn anything. Iteratively play again the best fixed version of itself. This might be a possibility. The third option is play against a supervised agent trained on demonstrations of best human players. Of course, in a game like chess or in a game like Go, there are so many possibilities that finding a supervised agent which is trained on demonstrations of best human players is something that is infeasible. And watch thousands of games being played and learn the patterns in an unsupervised manner, again that is infeasible, because you don't even know, even if you watch thousands of games, you might end up in a situation of chess which you have not seen in any of the 1000 games that you have learnt your unsupervised algorithm on, and therefore these three options of course will be wrong. Iteratively play against the best fixed version of itself is something that is done. What is done is, you first train this RL agent to play, and so the RL agent learns to play by itself. What it does is, you know that once it whenever it takes some correct move, you give it a plus reward. Whenever it does a bad move, you give a minus, you penalize the particular RL agent. So with time, after hundreds of iterations, it will learn to do something. It will not learn to play the game of chess perfectly or the game of Go perfectly, but it will learn to play it at least a bit better than it had started out with, and therefore it will start to play a better version of the, it will start to play it a bit better. And if you iteratively do this, so let's say you train it for 100 or 1000 such games, you keep it, you fix that RL agent, and now you employ that RL agent against itself, where this version is fixed. So the adversary in this case would be fixed, and the other RL agent will be playing, and so on and so forth. So you iteratively play against the best version of itself, so that it learns slowly. So iteratively play against the best version of itself is the correct answer. Okay, so yeah, so the questions were pretty simple and straightforward. So any doubts? Okay, so if you have no doubts, then I will close the session, and so you can ask me any questions from this week. can you explain one numeric example of the inequality? Okay, I guess you are talking about this particular inequality. So it is very difficult to explain numerically for this particular inequality, but I'll give you the idea behind it. So what happens is, okay, let me try to see whether I can. Okay, so I am just constructing an example here. So let's say I have a coin, and the probability of heads for that particular coin is 0.6, probability of tails is 0.4. So it's a biased coin, and and you take so basically what you will do is you will take the number of heads. So you will toss this coin multiple times. So you have got this coin, you will toss this coin multiple times. Let's say you have tossed this coin 100 times, and you try to get so yeah, you toss this coin 100 times and you get something like, let's say 70 heads and 30 tails. You get 70 tails and 30 tails, 70 heads and 30 tails. Based on this, your estimated probability of head would be 0.7. Okay, so what this inequality says is that the probability, okay, okay, let me change something. Let me make this to be p. Okay, the probability of p minus p hat, right, p minus p hat greater than gamma, which is up to you, is less than equal to 2 e to the power minus something, minus 2 gamma square m. Okay, sorry, minus 2 gamma square m. So what this here m will stand for, here m is 100 because you have taken 100 tosses. P would be, p you know to be 0.6, this you know to be this you have calculated to be 0.7, and gamma is something that you want. Let's say you have 0.05. So where this comes of use is, let's say, but this p actually is unknown to you. Here you know that p is 0.6, but this p is actually, you have just been given a coin and you have tossed it 100 times, you have got 70 heads and 30 tails. So this is p minus, let's say 0.7 greater than 0.05 is less than equal to 2 e to the power minus 0.05 whole square into let's say okay, let's say I have fixed this to be yeah, this is 100. So so if you compute this, then you are sure that whatever you have estimated is not far from the actual p by, I mean it is within 0.05 of p. So if p is this value, if this is p, then you are between plus minus 0.05 of this p plus 0.05 and p minus 0.05 of this. Okay, so that is the main idea behind this particular inequality, and yeah, so that is the intuition that you can get. I mean more yeah, so I guess that is sufficient for understanding what this inequality does. And if you see here that if m increases, so let's say instead of 100 this becomes 1 lakh, then of course this value goes on, it has come down immensely because this is e to the power minus 1 lakh, so it is almost 0. In this case you will also see that if this goes to 1 lakh, then this 0.7 will also become very close to 0.6. So this if you toss the same coin for 1 lakh number of times, then this probability of 0.7 would come down and would be very close to 0.6. and that also shows up from this particular inequality. Okay, I hope constructing explicit numerical examples might be difficult, but this is the intuition behind this particular inequality. Any other questions? Okay, if there are no more questions, I'll close this session. Next week would be the final session of this course. I mean, this is the last week which I covered. Next day I will have some around 8-9 questions or 10 questions maybe from the entire syllabus, which I might find to be important or bit more difficult, and I'll solve those, and that would bring me to the end of this particular course. Okay, then thank you, and next week we'll meet at this we'll meet at 7 p.m. Saturday. Thank you.
Thank you so much.
Thank you. Yeah.
Thank you, Soumya.
Thank you.